الآن بسم الله الرحمن الرحيم. هذا الحل assignment number 4, and I will begin with question number 1. And question number 1 says an induction motor draws 95 kilowatts, so the active power of the motor is 95 kilowatt. It's a three-phase line power supply with a power factor of 0.72 lagging. Number A, calculate the value of apparent and reactive power observed by the motor. So we have two things to find: the apparent power, which is the active power divided by the power factor. So 95 divided by 0.72, and this will give me about 131.94 ampere volt ampere, which is the reactive power. Kilovolt ampere. So Q, which is the reactive power, will be the square root of S square minus P square. So it's going to be square root of 131.94 squared minus 95 square, and this will give me about 91.55 kilowatt. So we found what we have been asked in A. Now in B, if a 25 kilowatt three-phase capacitor bank is connected in parallel with the motor. So the Q of the capacitor is 25 kilowatt. It will be connected in parallel with the electric motor. So what will happen? What is the new value of PQ supplied by the line? The active power will not change. It will be 95 kilowatt. The only thing that will change is the reactive power drawn from the source, and this will equal to the reactive power drawn by the source by the motor without the capacitor bank, minus what the capacitor bank is supplying to the load. So we will have 66.55 kilowatt that will be taken from the source. So now the new power factor. What is the new power factor? If we have been asked to find the power factor, this is not asked in the question, but it will be the new S, which is square root of the 66.5 squared plus 95 square, and here it will be 95, which is P, and we will have a power factor of greater than 0.72. For question number 2, an industrial plant is supplied by a dedicated 12 kilometer. So the length of the conductor is 12,000 meter, and the voltage V line to line is 34.5 kilovolt. The plant draws an active power the active power drawn by the plant is 1230 kilowatt, or 1.23 megawatt. The power factor here of the plant is 0.66 lagging. So the question is, determine the reactive power drawn by the industrial plant from the primary feeder. So to find the reactive power, first we need to find S, which is S square minus P square. So S will be P divided by the power factor, and it will be 1230 kilowatt divided by 0.66, and this will give me 1863.6 kilovolt ampere. The reactive power will be equaling to 1863.6 square minus 1230 kilowatts square, and this will give me about 1400 kilovar. This is for A in the question. For B, it said if a three-phase capacitor bank of so this is the Q cap of 1000 kilovar, 1000 kilovar is connected in parallel, is connected at the surface entrance of the industrial plant. So calculate this is B, this is A, determine. Okay, so we have been asked to find the power factor of the primary feeder after installing the capacitor bank. So the Q new is 1400 minus 1000, which is, this is given by the capacitor bank. We will end up consuming 400 kilovar from the utility. So the new S will equal to the square root of 1230 square, which is B square, plus Q square, which is 400 square, and this will give me 1293 kilovolt ampere. This is the apparent power supplied by the source. So the new power factor will equal to 1230 divided by 1293. So the new power factor will be 9.95. So the power factor increase from 0.66 to 0.95 by adding a capacitor bank of 1000 kilovolt. Now for B, part B, the active and reactive power supplied by the primary feeder after installing the capacitor bank. So P will not change, it will be the same, 1230 kilowatt. The new Q will be 1400 minus 1000. The new Q is 400 kilowatt. For part C, if the conductor of the primary feeder have a resistance of, so we have a resistance of 47.75 ohms per phase, determine the power losses in the primary feeder before installing the capacitor bank and after installing the capacitor bank. So A, it will equal to IL will equal to P over square root of 3 V line cosine theta. So 1230 kilowatt, which is 10 to the power 3, divided by square root of 3 times 34.5 times 10 to the power 3 kilovolt times the power factor, which is 0.66, which is 31.19 ampere. So the power loss will be 3I squared into R, so 3 times 31.19 squared times the resistance, which is 47.75, and this will equal to 39.36 kilowatt. This is the losses in the line. For B, after installing the capacitor bank, the power factor improved, so 1230 times 10 to the power 3 divided by root 3 times 34.5 times 10 to the power 3 times the power factor, which is 0.95 instead of 0.66, and the ampere reduced to 21.67 ampere. So reducing the current value will reduce the losses, which is 3 times 21.67 squared times 47.75, and this will equal to 21.67. Oh, sorry, it will equal to 67.27 kilowatt. For part D, explain the advantages of installing a capacitor bank. By installing capacitor bank, the electrical power drawn from the primary feeder will reduce. What I mean about this, the reactive power drawn by the primary feeder will reduce, reducing line currents and power losses in the line, and the line voltage drop will also reduce. So installing capacitor will improve the power factor. Number 2, reduce the line current. Also reduce reactive power drawn from the primary feeder or from the source. And number 4, this will reduce the losses. And finally, improve the voltage regulation. That is the end of assignment number 4. Thank you.